welcome to our tutorial, our web tutorial over the beginning of our Unit 5 Forces 2. We are going to be taking notes today on a sheet of notebook paper. You need to number it 55 and title it Science Note. If you were absent on Tuesday, October, November the 8th, you need to make sure that you pick up your Signs worksheet from your hanging file folder. Okay, so let's go to the next page. So we have talked about static before, static friction, but we're going to talk about static equilibrium in this first part of this unit. Static means to be stationary or at rest. Static equilibrium in the case of forces is when all the forces acting on a body are balanced and the body is not accelerating. So an object that is in equilibrium is going to be either at rest, which means it's staying at rest, or it may be in motion but moving at a constant velocity or speed. Okay, speed includes direction. So let's look at these two figures. Are these objects in equilibrium? So right here we have two free body diagrams. One free body diagram has an F of G and an F and N of 50 newtons. Is it at equilibrium? On the F of F and the F of A side, it's both 30 newtons. So maybe you're thinking yes, and then maybe after I said what I did, you're thinking no. Well, so which is it? It is at equilibrium. Now remember, our x and our y components are independent of one another, and we've talked about that in a unit before. And even in our forces, they're independent of one another as well. So the forces are considered in equilibrium if the forces in the x direction are balanced. So on our first figure, looking at our x direction, which is also our horizontal, our F of F and our F of A are both 30 newtons. If you try to subtract them, you get zero. So your net force is zero. So yes, it is in static equilibrium. If you look over at the second free body diagram on our horizontal direction or axis, we have a 75 Newton for F of F and F of A. So 75 minus 75 is zero. Here again, we have a zero net force. So our x direction on both of the free body diagrams is equal. So therefore, we have a static equilibrium. And then if we look at the y component, or the y direction, also called vertical, on the first diagram and the second diagram, our f of n is 50 and our f of g is 50. 50 minus 50 is 0, and so we end up getting a 0 net force. So keep in mind, it does not necessarily mean that all the forces are equal to each other when we look at them to y to x component. They just have to be equal on the x component, and they just have to be equal on the y component. Okay, so let's move forward. Now, our lesson for today is about signs, and we're specifically talking about signs that are hanging. They're usually hanging from a wire. So signs hanging from a wire, chandeliers hanging from wires, and the like. If the object is stationary, and for our purposes, all of these sign problems are going to be stationary, the forces in the x direction have to balance, and so do the forces in the y direction, so that we can figure out what the actual force is. So we're totally ignoring any wind that may be causing these things to blow. Now, the two forces are going to involve the signs. that are going to be involved with for the signs are going to be our weight, which is our F of G, and remember our F of G is calculated with the mass and the gravity due to acceleration, which is always 9.8 meters per second squared. So if we're just given the mass of the sign, we can find its F of G. Now the F of G points straight down. Then we have the tension. The tension force is the force that is required to hold the object up. So as we did with just objects that were still, our tension force is like our F of N. And remember, when we would do our free body diagrams, our F of N and our F of G were the same, okay? And so we're going to use that similar concept when we talk about hanging objects. So instead of calling it the F of N, we call it the capital T. Okay, so let's move forward. So example one. So here's an example. If you don't have your notes yet, this is on the note sheet that you will pick up in your hanging file cabinet or your homework examples. Example one, there is a 260 Newton sign that hangs by a wire. As we see right here, it says welcome to College Station. We want to know what the tension in the wire is. Well, remember when we did our free body diagrams, we know that the sign is 206 newtons. So that is its F of G. So F of G is the force that gravity is putting on it, 260 newtons. And so there is a tension force from the wire of 260 newtons as well. Okay, so that's cool stuff. Now, unfortunately, they're not all going to be that easy because they had to make it difficult. A little bit, it's not real difficult. Example 2 tells us that we have two wires now that are holding the sign up. If we have two wires that are holding the sign up and the sign is still 260 newtons, that's its FG, then we are going to take the FG, which is 260 newtons, and we're going to divide it by 2 because we have two wires. And so our FT, or our T, for each wire is going to be 130 newtons. So this one's 130 newtons, and so is this one. Okay, cool stuff. Well, now we're going to get a little bit more difficult with it because, you know, when triangles are involved, um, it's really amazing how they can help us understand how weight is distributed with things. So we're going to come back to our x and y components, which are nothing that we've not ever done before. We still find the sides of a triangle with trigonometry like we always have. So when we have a hanging object that has an angle, what we've got is a rope or a cable that makes an angle with the ceiling or the beam or whatever it is that the sign is going to be hanging from. So the weight is only equal to the y component of the tension. So remember, the tension is the up, the Fn direction, if you will. The x component doesn't matter to us since all of our problems are going to be at equal angles. So it's going to cancel out. So we don't have to worry about the horizontal. We're just going to be calculating that y component. In this case, our y component has a special name. Okay, our y component is called capital T little y. So we've got some steps here that we're going to use in order to calculate our resultant. So in these particular examples, we're trying to find our resultant. So step one is going to be to find our ty. Our ty would be the invisible line that we would draw of the y component, and it's in the middle of the angle that is made with the wire the sign that makes. That doesn't make sense. That the wire is used to hang the sign is making that angle. Okay, so there's two sides of it. It's still one piece of wire, but there are two sides, and you can see if we put that invisible ty component through, that's my dotted red, I've got this side of the angle and I have this side of the angle. So I have two sides of an angle. Now because those sides or those angles are equal, okay, whatever I calculate for big T is going to be the same over here for this black line. So let me erase this stuff. So you see the seafoam green. This is big T, seafoam green. That's the big T. And this black line over here is also a big T. But this big T and the big T over here will end up being the exact same number because they are triangles that are exactly the same. Okay, so the first thing is, just like we said earlier, if there are the mass of the object or the force of the object is going to be divided in two if there's more than one side of the rope. So although we only see one ty, there's actually two ty's because we have two triangles, and one triangle has to have three sides. So I'm going to put a little green line right here on this side to represent one ty, and I'll put a little blue line on this side to represent the other ty. So what I end up doing is I take the force that they give me, which is always or typically going to be the F of G, and if they don't give me the F of G, they'll give me the mass. And if I'm given the mass, then I just use the acceleration due to gravity to find my F of G. And my Ty is going to be the same of the F of G. But to find Y, we have to take that F of G and divide it by the weight, or excuse me, divide that weight by the number of ropes. Now, even though this is, like I said earlier, one rope, it makes an angle, and it makes a two-sided angle, which requires us to have to do trigonometry and look at it this way. Step two, we have to figure out if ty is the opposite, the adjacent side of the angle. Okay? Now, the way that we're going to know that is in the question, they're going to tell us where this angle is exactly. So we're going to look down here at the bottom of this slide. At the bottom of this slide right here, we see t equals ty divided by sine of the angle, or t equals ty divided by cosine of the angle. Okay? If we are told below the horizontal, that means this right here is the ceiling or below the ceiling, and then they give you an angle, that's where we're coming from. So there's the angle. From that point, that is how we're going to find out who the sides are of the triangle. We know that this seafoam green is always going to be big T, which is the hypotenuse. Okay. Step 3 tells us that we're going to solve for big T by using one of these two formulas. What is big T? It is the hypotenuse, also known as the resultant. And we've been doing resultants since unit 1. Okay, so you know these terms. So big T is the same thing as the hypotenuse. Okay, here is my angle. If they tell me that my angle is below the horizontal, then I know that this is my adjacent and therefore this is my opposite, which is already there, but that's how you figure that out. So if I want to find my hypotenuse, I've got to solve for h. And so basically all we have done is we've taken this formula, sine of the angle, which is opposite divided by hypotenuse. Remember? And then we do rearranging of this formula. I've got to divide both sides by h. The h cancels out over here. I'm going to rewrite this. H is not by itself, so to get h by itself, I'm going to divide by sine of the angle. That cancels out, and I get h equals O over sine of the angle. And that's exactly what that is. It's just that, let me erase this. It's just that t is the same thing as h, and ty is the same thing as the opposite. Okay? So there's that situation. There's another situation where your problem may say to the vertical, and if it says to the vertical, it's referring to the angle being down here. Okay, and that's closer to the sine itself. So if my angle is down here, and I always know that this side is my big T, which is also my hypotenuse, therefore this is my adjacent and this is my opposite. So when I want to solve for my hypotenuse, which is h, I am going to take my h and a. That is going to be cosine of the angle, which is adjacent over hypotenuse. I have to solve for h, so I got to get h in the numerator position. Divide by cosine because I got to get h all by itself. And there's my formula. And look, it's the same as this because big T and big H are the same. Big TY is the same as adjacent. So with that, let's do a problem. You pause this as you need. So we have a sign that says welcome to College Station. And the one rope makes two sides. So essentially I have two sides, two ropes. I have to look at it that way. And I'm going to go ahead and draw the free body diagram here. So this is my F of G, and my dotted line is going to be my T of Y. And my T of Y is the same thing as my F of G, but I have to divide it by 2 because I have two big T's, okay, which are my hypotenuses, my resultants. So my sine is still 260 newtons, okay? I have to divide that by 2, which is going to give me 130 newtons for one side. So this is my TY. Okay, I followed step 1. Easy stuff. The angle that is formed is 40 degrees from the vertical. So I'm going to take my triangle on the right and I'm going to blow it up for you so that you can just see what I'm doing. All right, so this is my big T, which is also my hypotenuse, right? It said the vertical. So the angle is formed from the vertical, which is down here, 40 degrees. Okay? So that means that this invisible line is my big T, little y, which we already discovered is 130 newtons because we had to divide the FG of the sine and by 2 because there's two sides there. Okay, and so now I just have to identify which sides of the triangle are what. I already know that big T is my hypotenuse. So if my angle of interest is in the very bottom angle, that means that the left side of it is the adjacent. Okay, so therefore the very top part, which would be the ceiling, is my O, my opposite. So I take my, if you haven't memorized this by now, remember there is this that you can use, SOHCAHTOA, and I know that I need to find H, and I already have A. So H and A, I look over here who has H and A in it. This does, so that's cosine of the angle. So I get H by itself. Okay, remember I'm going to do this all in one felt swoop. So my H is my A, 130 newtons divided by my cosine of the angle, which is 40 degrees. And that you will get 170 newtons. And that is how you calculate the tension force for a sine. Thank you for joining the web tutorial.